Hello everyone. In the second half of this chapter, we're going to look at the polarity of molecules, valence bond theory, and hybridization. So how do we determine whether a molecule is going to be a polar molecule or a non-polar molecule? Well, the very first thing that you want to do is to draw the Lewis dot structure of the molecule and then determine whether the individual bonds are either polar or non-polar. So let's look at an example here. So we have hydrogen fluoride, a molecule, right? So we have a hydrogen that's bonded to a fluorine. And we know that this bond between hydrogen and fluorine is a polar bond. And the reason why is because of the fact that we have two different elements with two different electronegativities, where fluorine is the more electronegative atom. So if you remember from the previous lesson, the trend in electronegativity basically increases in the periodic table from left to right towards fluorine, and then from bottom to top towards fluorine, because of the fact that fluorine is the most electronegative element in the periodic table. And so we know that this bond between hydrogen and fluorine is a polar bond because of the fact that they have a net dipole, right? The difference between the electronegativity between hydrogen and fluorine is non-zero, and so therefore this bond between them is polar. And here's another example. So we have the Lewis dot structure for carbon dioxide gas. We have carbon versus oxygen. Oxygen is more electronegative than carbon, and so because of the difference in their electronegativities, this double bond between carbon and oxygen is polar. And because oxygen is the more electronegative atom, this atom receives a partial negative charge and carbon the partial positive charge. So you have a separation of charge known as a dipole. And so the dipole, the net dipole, is basically non-zero, and that's what makes this double bond polar. And same thing over here, this double bond between carbon and oxygen on this side is also polar. And here's a third example here. We have the Lewis dot structure for carbon tetrachloride, CCl4. And as you can see, chlorine has a higher electronegativity than carbon. And so they will have a separation of charge in which the chlorine, the more electronegative atom, will receive the partial negative charge, and the less electronegative carbon will receive the partial positive charge. And so this bond between them, the carbon to chlorine bond, is going to be polar. So all of these single bonds are all polar. And here's a fourth example. We have boron trifluoride. This is the Lewis dot structure for BF3. Again, fluorine is the most electronegative element in the periodic table. And so this will receive the partial negative charge and the boron the partial positive. And because again you have that separation of charge, you have a dipole, a net dipole. So this bond will be considered polar. Every single one of these single bonds will be considered polar. All right, now, so how do we determine whether the molecule is polar or non-polar? Well, the first thing that you want to do here is to determine the direction of the polar vector, as they call them, right? So the polar vector for hydrogen fluoride is going towards the more electronegative element, which is fluorine. And so you're going to draw an arrow with a positive tail here. And this arrow points towards the more electronegative fluorine. And so because this is the overall direction of the polar vector, we have a polar molecule. And so hydrogen fluoride is a polar molecule. Now, what about carbon dioxide? So we have carbon to oxygen bond and another carbon to oxygen bond on the right. And so we know that this oxygen on the left is more electronegative than the carbon. And so we would draw a polar vector that's pointing towards oxygen. Okay. And so because we have two polar vectors here, and they're pointing in opposite directions, then these two vectors will be canceling each other out. Okay, and because they're canceling each other, the net dipole of this overall molecule is going to be zero. And so therefore, carbon dioxide is a nonpolar molecule. And we can do the same thing for carbon tetrachloride. So you can see here that we have 4 chlorine atoms, and the chlorine atoms are the more electronegative atoms here compared to carbon. And so when you draw the polar vector, it would be pointing towards the chlorine atoms, right? So you have 4 different polar vectors that are pointing towards the chlorine atoms. And so when you add up all these polar vectors together, what you have is what they call resultant vector. And this is basically the net dipole. So the net dipole here is also going to be 0 because they're all going to be canceling each other out. And so carbon tetrachloride is therefore a nonpolar molecule. And the last one here at the bottom is boron trifluoride. And so we have polar vectors that will be pointing towards the fluorine atoms. And the resultant vector, or the net dipole here, is also going to be 0. And therefore, this molecule is going to be nonpolar. Now, what if we replace one of the fluorine atoms with, let's say, a less electronegative element, like hydrogen? Okay, what would be the polarity of this molecule? Well, now we know that this bond here between boron and hydrogen will be less polar compared to the bond between boron and fluorine, just because of the fact that the difference in electronegativity between hydrogen and boron is lower than the difference in electronegativity between boron and fluorine. Okay, and so when you draw the polar vectors, you have 2 polar vectors that will be pointing towards the more electronegative element, and then this smaller polar vector that's pointing towards boron. Okay, this vector is smaller because of the fact that the difference in their electronegativity is lower. Okay, so now when you add up all these polar vectors, the net dipole moment, the net dipole, is going to be non-zero. And so because the net dipole moment is non-zero, this molecule is going to be considered a polar molecule. So again, how do we determine the overall polarity of molecules? Well, you have to look at the polar vectors and add them all together to get the resultant vector. So if the resultant vector is equal to 0, then that molecule is going to be nonpolar. But if the resultant vector is non-zero, then that molecule is going to be polar. If you haven't taken calculus or physics, then most likely you've never heard of this concept known as vectors. But if you have, then you can skip this part. So vectors have a numerical value known as scalar quantity and direction. Here's an example: velocity versus speed. Velocity has a numerical value and direction, whereas speed only has the scalar quantity. So because velocity has both direction and quantity, we have a vector, whereas speed only has a quantity or scalar quantity, therefore does not count as a vector. So let's say, for example, that you're driving a car and you're turning. This actually is a perfect example showing you the difference between velocity and speed. So when you're turning here, you can have a constant speed, but not a constant velocity, right? So you can go at 20 miles per hour turning on a curve, right? So that's a constant speed because your speed is not changing. But because velocity is both a scalar quantity and or has both direction and scalar quantity, you can have a constant speed, but the direction is changing. And that's why velocity can never be a constant value when you're turning on a curve. So how do we add 2 vectors together? Well, here's a scenario. As an example, we have 2 cue balls that will simultaneously collide with the 8th ball. So the question here is, in which direction would the 8th ball go? Well, in order to determine this, we have to add the 2 vectors. So the first cue ball has a force called F1, And the second cue ball also has a force known as F2. Okay, so how do we add the two vectors together and find out which direction the eighth ball will go? So in order to add the two vectors together, we can use this method known as head-to-tail addition. So we're going to draw the first vector, F1, and then connect the head of F1 to the tail of F2, as shown here. And then we're going to connect the tail of F1 to the head of F2, and this is basically the resultant vector. So this is the third vector, which is the result of the addition of the two vectors. So it has this specific scalar quantity and direction. So it would be going in this direction. And again, this is known as the resultant vector. And if you have, let's say, two opposing vectors with the same scalar quantity, meaning the same length, then what you have is a zero resultant vector. So you have a net resultant vector of 0. So let's take a look at this one example again. Here we have carbon tetrafluoride, where fluorine is the more electronegative element. And so when you draw the polar vector, it would be pointing towards fluorine. And all these single bonds right here are equal in scalar quantity, meaning the difference in electronegativity will be the same because it's all the same atoms, fluorine, that's connected to the central atom. And so that means that the scalar quantity here will be the same for every single polar vector. The only difference is the direction. And so because they're all pointing in the opposite direction, when you add these vectors together, you get a resultant vector of 0. So in that case, this molecule is considered nonpolar. And this resultant vector is also known as dipole moment, and it has this symbol which is similar to a microsign. Now, what if we replace one of these fluorine atoms with a less electronegative atom? Let's say, for example, iodine. So iodine is a less electronegative atom, and so when you draw the polar vectors, they would be pointing towards fluorine. And we have this tiny little polar vector here because the difference in electronegativity between carbon and iodine is very small. And so when you add the polar vectors together, what you have is a non-zero resultant vector. So in other words, this molecule is going to be polar. And here's another example. We have the Lewis dot structure for ammonia, NH3, with the proper bond angles. Okay, so I've already taken into account the molecular geometry here. And so when you're determining the polarity of a molecule, make sure that you take into account the bond angles, the molecular geometry and the bond angles. So here we have a lone pair right above nitrogen. And so if you have a lone pair, this is obviously more electronegative than anything else because you have electrons. And so the polar vector would be pointing up towards the lone pair of electrons. And because nitrogen is more electronegative than hydrogen, the polar vectors for these angles, for these bonds, would be pointing towards nitrogen. And so the overall resultant vector here would be non-zero. And so therefore, ammonia is considered a polar molecule. So now let's take a look at a more advanced bonding theory here, known as valence bond theory, or VB theory. So this theory basically explains how covalent bonds form via atomic orbital overlap. So it uses this concept of hybridization of the atomic orbitals. But regarding hybridization, our focus here will only be on the central atom instead of the terminal atoms. So let's look at the bonding in this molecule, beryllium chloride. So we know that beryllium is going to be the central atom, and that it has 2 valence electrons because of the fact that it's in group 2 in the periodic table. And when you draw the orbital diagram for beryllium, just for the 2 valence electrons, it would look something like this, right? So you have the 2 valence electrons on the 2s. So the 2 electrons are in the 2s orbital. And the 2p orbitals are completely empty. And so you would expect beryllium to be completely stable, right? Because it has paired electrons. You would expect that beryllium is going to be incapable of bonding, incapable of forming a bond with any atoms because of the fact that both electrons are paired. And so, how does valence bond theory explain the ability of beryllium to form bonds with other atoms? Well, according to this theory, valence bond theory, the atomic orbitals of beryllium, the central atom, will form a hybrid. And this is what they call hybridization, the method of hybridization. And so what does that mean exactly? Well, the 2s and one of the 2p orbitals will form hybrid orbitals. Okay? And so the number of hybrid orbitals formed is equal to the total number of valence electrons of the central atom. And so because beryllium has 2 valence electrons, it will form a total of 2 hybrid orbitals, namely the 2s and the 2p. Okay, so one of the 2s and another one of the 2p orbitals. So what does a hybrid orbital look like? Well, for beryllium, we have 2 valence electrons, and so that means that the 2s and one of the 2p orbitals will combine and form a hybrid, and so we would call that sp hybridized orbitals. Okay, and again, because you have 2 valence electrons, it will form 2 sp hybridized orbitals, as you can see here. And these 2 hybrid orbitals are now degenerate in energy, meaning the same in energy. And so what about the unhybridized orbitals, the 2p? So you have 2 2p orbitals up here, which are higher in energy, and these 2 unhybridized orbitals are empty. So they're not occupied by any electrons. But these 2 hybridized orbitals are now occupied by a single electron. Okay, and again, we have to follow Hund's rule, right? Before you start pairing up the electrons, make sure that you fill the orbitals singly first. So now we can explain that beryllium can form 2 bonds, right? So this hybridization of orbitals explains the formation of 2 bonds for beryllium. Here's another example here. We have boron trifluoride, BF3. Boron's going to be the central atom, and boron has 3 valence electrons. So when you draw the orbital diagram for these 3 valence electrons, it would look something like this, right? 2 electrons in the 2s and 1 electron in one of the 2p orbitals. According to the Vesper theory, 3 equivalent single bonds will form between boron and fluorine. And so how can valence bond theory explain this? Well, again, we will have to form hybrid orbitals. Okay, 3 valence electrons, 3 hybrid orbitals. So it would look something like this. So the 2s and 2 of the 2p will form hybrid orbitals. And we call this sp2 hybrid orbitals. So the number 2 up top basically tells you how many p orbitals will form a hybrid. And so in this case, we have 2 p orbitals that will form and 1 s orbital. And so we have a sp2 hybrid orbitals. So these are your hybridized orbitals, and you have 1 2p orbital that remains unhybridized. And again, so now we can split all 3 valence electrons among the hybridized orbitals, as shown here. So now you can see that these hybridized orbitals can form 3 single bonds with fluorine. So here's another example. We have CH4, which is methane gas. Carbon is going to be the central atom, and it has 4 valence electrons. And when you draw the orbital diagram for the 4 valence electrons, it would look something like this. So we have 2 electrons in the 2s and 1 electron for each 2p orbitals. And according to the Vesper theory, carbon will form 4 equivalent single bonds with hydrogen. So valence bond theory explains this by saying that 4 atomic orbitals will form a hybrid. Okay, so 4 atomic orbitals will be hybridized, and now it would look something like this, right? So you have one orbital from the 2s and all 3 2p orbitals all together will form 4 hybrid orbitals, or 4 hybridized orbitals. And this is called sp3 hybrid orbitals because of the fact that you have 1s and 3 p orbitals, sp3. Okay, so now you can separate these 4 electrons, 4 valence electrons, 1 per hybrid orbital. And shown here at the bottom is basically the hybridized orbitals. So the carbon has 1, 2, 3, 4 sp3 hybridized orbitals. So here's 2 more examples. We have PF5 and SF6, phosphorus pentafluoride, and sulfur hexafluoride. So we know that both phosphorus and sulfur can have an expanded octet, meaning can have more than 8 valence electrons. And the reason why is because of the fact that they are on the 3rd row in the periodic table. So any elements on the 3rd row and below can have an expanded octet. So in PF5, phosphorus is the central atom, and we know that phosphorus has 5 valence electrons. And so when you draw the orbital diagram for phosphorus, it would look something like this. We have 2 electrons in the 3s and 1 electron per 3p orbital. And so because phosphorus has 5 electrons, 5 valence electrons, then it's capable of having 5 hybrid orbitals. But as you can see, we only have 4 orbitals here. We have a 3s orbital and 3 3p orbitals. And so how can phosphorus have a 5th orbital? Well, it can start accessing the 3d orbitals. So in that case, phosphorus will have 5 hybrid orbitals. 1 from the 3s, 3 from the 3p, and 1 of the 3d for a total of 5 orbitals. And so these hybrid orbitals are now called sp3d orbitals because of the fact that there's 1 d orbital that's included in the hybridized orbitals. And the rest would be unhybridized orbitals. So now you can separate all 5 valence electrons and distribute them evenly in the sp3d hybridized orbitals, as shown here. And this is what the Lewis dot structure looks like. And these bonds right here, every single bonds that's formed between phosphorus and fluorine is known as sp3d hybridized orbitals. What about for SF6, sulfur hexafluoride? We know that sulfur is going to be the central atom, and sulfur has 6 valence electrons, and so that means that it will form 6 hybridized orbitals, and so it will start accessing the 3d orbitals as well. And so you will have 1 3s orbital, all of the 3p orbitals, and 2 of the 3d orbitals. So that's a total of 6 hybridized orbitals. All right, so the remaining number of unhybridized orbitals would be these 3 right here. All right, and so the hybrid orbitals are now known as sp3d2 hybrid orbitals because of the fact that you have 1 s orbital, 3 p orbitals, and 2 d orbitals. So now you can evenly distribute all 6 valence electrons in these hybridized orbitals, as shown here. So all of these single bonds that's formed between sulfur and fluorine are called sp3d2 hybridized orbitals. Here's an easy way to determine the hybridization of the central atom. All you have to do is count the number of electron groups. So for example, carbon right here has 2 electron groups, and so the hybridization of the bonds would be sp, right? 1 s orbital and 1 p orbital, which is equivalent to 2 electron groups. All right, so for boron here, this boron, the central atom, has 3 electron groups, 1, 2, and 3. And so the hybridization would just be sp2, 1 s and 2 of the p orbitals, for a total of 3. All right, for sp3, ammonia would be a perfect example. This nitrogen right here has 1, 2, 3, 4 electron groups. And so the hybridization would just be sp3, 1 s orbital and 3 of the p orbitals equals 4. All right, and for the next one here, we have SF4. When you count the total number of electron groups for the central atom sulfur, we have 1, 2, 3, 4, and 5. Remember that a lone pair counts an electron group. So that's 5 electron groups. And the hybridization of the bonds in the sulfur would be sp3d1 or sp3d. Right, so 1s, 3 p's, and 1d. When you add them all together, you get 5. And the last one here is xenon tetrafluoride. So each of the bonds that's formed in xenon is sp3d2 hybridized. And when you count the total number of electron groups for xenon, we have 1, 2, 3, 4, 5, and 6. And so when you the hybridization of the bonds would just be sp3d2. Again, when you add them all up, that should equal 6, right? 1 s orbital, 3 p orbitals, 2 d orbitals, for a total of 6 orbitals, which is basically the number of electron groups.